Perfect. Yeah. So when I was asked whether I wanted to speak here, and they said, yeah, just speak about whatever you do. Large deviations is what I do, but I understand that even though it is addressing similar problems that people had all of this week and that were addressed all of this week, it's very different in style because it's in essence sample free. So I'm still interested in computing probabilities or in drawing from a measure, and in particular in problems where this is hard to do because events are maybe very rare, but the methods that I'm considering are such that I don't need to draw random samples, not even biased samples, but just solve it in an alternative way. So the idea of this is that I introduce into this from the beginning and through multiple different perspectives and show a few applications of that in the meantime that, as I said, in flavor are maybe very comparable to what we have seen, for example, the molecular dynamics problems that we've seen last time and so on, but I don't think can be treated with similar methods easily. So they will remain to be high-dimensional and complex systems, but I don't think they can be easily sampled with these Monte Carlo methods that we've seen. Right. So this all concerns ray events, and I mean, I speak for such a long time, I should maybe tell you also why I care about ray events at all and what I mean with them. So what we have is some kind of stochastic system or some kind of complex system, maybe not even stochastic, but just chaotic or something. And some events can happen in this system that are of extremely low probability, sometimes very low probability, 10 to the minus 10 or something, but we might still care about them because they are very important, they are very relevant. So typical examples would be some kind of earthquake, stock market crashes, plane crashes, and so on. They are very low probability, but they have a high impact. So if you maybe naively multiply your perceived impact with the probability, the resulting number is still high, even though the probability is very low. So you still care about these events, even though they are of extremely low probability. And the ones that I'm mentioning here, earthquakes, stock market crashes, plane crashes, and so on, are maybe very hands-on, and it's clear that we maybe should care. I mean, stock market, I'm not sure, but they concern lives of people, so yeah, obviously this is very important. But of course, this is not the only class of problems that you have, and the one that we heard a lot is that you have some kind of separation of scales between maybe the internal time scale of the thermal fluctuations, which, I don't know, I'm not a chemist, femtoseconds or picoseconds I heard the other day, but I'm not sure whether it's true. And then the time scale on which the chemical reaction itself happens, which is orders of magnitude larger. So on the time scale, on our time scale, these events look ubiquitous, they're just chemical reactions, but on the internal time scale, they are extremely rare. So chemical reactions, maybe also bit flips from cosmic rays, where you say, okay, it's very unlikely that the cosmic ray hits exactly this bit in my hard drive, but I have 10 to the 9 bits in my hard drive, and then it's much less of a surprise that this is a thing that you should consider and then you should care about. So you always have this separation of scales where, yes, the individual thing is very, very rare, and you might think you shouldn't care, but then you have either so many trials or so many copies of your system that they don't become relevant at all. So here I have this typical picture where you have some kind of barrier crossing event, and then you can reduce this to like a more mathematical fundamental one where you have a double well. I always like to use this picture because this is the, I call it the most expensive double well because this is the Warwick logo. And I think they paid a 5-digit amount for, no, 4-digit amount I think for the logo when they did the corporate redesign. No, it's 5. 5? Yeah. Oh, for the logo or for everything? Maybe 6. Maybe 6, yeah. So you have some kind of, I mean, okay, how many lines is it? 6 lines? Yeah. So you have some kind of well, and then you have a particle stuck in this well, and you ask how likely is it to jump to the other side. So this would be like a more abstract way of viewing the same things. Right. So where I'm coming from, I have a similar motivation that I often give when I'm talking to more applied people, namely climate change. So I mean, hopefully nobody in the room denies that climate change is happening, and we do care about human well-being in light of climate change and climate change-induced natural disasters. So what you see on the right is statistics over the last 10 years. So this is up to 2022, so not quite the last 10 years, but last 20 years, but long-time statistics of deaths that are attributed to natural disasters. It's not, of course, not obvious that all of these natural disasters have something to do with climate change. Maybe most of them don't, but the statistics we care about is death by natural disasters. So this is coming from some EU database which tracks these things, and of course there are many questions that you can ask. What counts as a death that is caused by something? It's not quite obvious. If there is a flood that causes a famine, that causes someone to be malnourished, to get sick, is that caused by it? But they count in whatever standard they count, and they count about 1.3 million deaths in the last 20 years, which sounds low maybe if you think about it that way, but these are the statistics, and they count a total of 7,972 events. So the point that I'm trying to make here is that I now take the same statistics and I just remove the top 10 events, then you get this statistics, the dark blue one. So this is 7,962 instead of 72 events, and I've cut the number of deaths by a factor 3. So most of the deaths, the majority of deaths, are caused by a few outlier events. So these are usually floods, heat waves, storms. They're not all the same looking. They are all very different looking, and it's only a handful that are responsible for most of the deaths regarding natural disasters. So I think there is a flood in Pakistan. Often there are storms or tsunamis or heat waves that cause a large number of deaths in a small time span. So the problem here is that, yes, we have climate models. Maybe we can simulate Earth to some degree of accuracy at least. Clearly not enough to be predictive, but maybe enough to get statistics. But these events are so rare, they're basically unprecedented. There is no data from observation, and you cannot really sample them because you have a climate simulation that way you're happy that you have maybe an ensemble of 3 or 4. But you would need an ensemble of a few million or billion in order to observe these events once. And of course, this is maybe very related to the problems that we see all week, where you say this is a difficult sampling problem. I should maybe not do naive sampling. I shouldn't just blindly run billions of climate simulations and then hope that I see these events. I should do some biasing, or I should do some smarter way of sampling. But of course, the systems are very different in nature. They are chaotic, they are non-equilibrium, which I guess means you can't really easily sample them. You don't have a reverse process available and so on. So they are very hard to sample. So I guess I want to make the point that large deviation theory offers an alternative, maybe not exactly for this problem, but for many of the problems that I'm about to show that are similar in flavor. So the central problem then throughout will be that these extreme events are very difficult to deal with in any complex system because they are too complex to have any analytical solutions. For the double, well, you can write this down, but obviously for the climate system or even for much simpler physical or chemical systems, you cannot write down an analytical solution for what's the probability of these events, but they're also too rare to be observed in any experiment or in any simulation. So, I mean, this is maybe closer to application than most of you, but you might even think of doing experiments for some of these things that I'm going to show, but even then they might be too rare to give you meaningful results. And it's, of course, much harder to bias an experiment than a numerical simulation. So, the consequence that's maybe obvious to anyone here is that these rare events must be treated in some special way, and you need to craft your algorithms in order to deal with them. And standard algorithms just solve them. So I'm coming from a numerics perspective, and I want to design algorithms that can deal with such situations more reliably than just doing naive sampling. Right. One fun example that I often start off with. This is a ship, and it's a very easy model of a ship. So you have the hull of the ship, and it has a center of gravity G, that's the red dot, and gravity pulls you down. But part of the ship hull is submerged in water, so it's buoyant. And there is a center of buoyancy, which I guess is the center of mass of the displaced water, which is not the same as the center of gravity of the ship hull. And if it's displaced and it has an upwards force, you get ship rolling. And in particular, hopefully you design your ship in a way that your upright state is stable, so that if your ship is upright, it will stay upright. And if you kick it slightly, the buoyancy force pushes you back upright. If you don't push it too hard, of course. So you might think a while about it. It's not quite so easy to think how the shape of the hull is related to the restoring force given a given rolling angle, but that's exactly what we are asking. We have a rolling angle phi, and if you push your ship a bit from the side, it will oscillate, and because there's friction, it will at some point stop oscillating. So you have a restoring potential V that in a complex way depends on the hull shape. So I don't know how these things are computed, but I guess engineers in marine safety design, or maybe just in shipbuilding, could fit these things from experiment. You can maybe measure stuff from experiments. You have a certain hull shape, and then you can get what's your restoring force given a given angle. Because if the ship hulls are not very simply shaped, and they are, then the way that the submerged area underwater increases with the rolling angle is a complicated nonlinear formula. So I postulate a friction coefficient as well, and I achieve these equations where I also generously added stochasticity for something to happen at all, because otherwise I would just sit upright. So I say I have a rolling angle. It's just the rolling angle develops with the rolling angular velocity and some noise. And I have the rolling angular velocity. There is the restoring force coming from the hull shape and from the uprighting from the buoyancy, a friction term, and another force. So maybe a physicist would tell me I shouldn't put two forces here. And in particular, maybe an engineer would tell me I shouldn't put white and time Gaussian noise in the Brownian walk, because waves are very different from white and time Gaussian noise, obviously. But that's just like a simple way of, okay, I have this system and then I add noise. And it's maybe quite surprising that this is probably already more sophisticated than what is actually done in marine safety design, where you have standards on how safe a ship hull must be against ship capsize, and they usually take such a model and then linearize them. Maybe. But of course, this is a problem of the double well kind, in a sense, right? Because you can think of the system, so now I'm plotting it in the phi dot plane, and the arrows are supposed to be the deterministic part of the dynamics. So I get these spirals, which just mean if I start somewhere here, which is an upright ship, but it has angular velocity, then it will spiral down to this point, which is the point where the ship is just upright. So in this direction I have velocity, and in this direction I have angle, and you see this point and that point, which of course correspond to, by just defining my angle 0 to be the upright position. On this half, the ship is the way that I want it to be, and on this side, the ship is capsized. So the problem that I'm asking here is, if I start in this green area, how will it look like, and how likely will it be, or what's the expected waiting time for my ship to capsize? And maybe even more precise, if it capsizes, how does it do so, and what was the corresponding noise that led to the capsize, meaning what are the waves that let me capsize more so than others. Of course, these will not be realistic waves, as I said. So of course, this problem is just two-dimensional. It's a two-dimensional SDE. I can easily sample this on my laptop, and I did. So this is a cloud of points where I simulated this system, I don't know, 1,000,000 times or something, starting here and showing only trajectories that end here. So these are all capsized trajectories of this ship rolling motion easy model. And what you see is that, yes, there is like a cloud around the stable state, the green state. This is where I start. But then eventually, because I conditioned on it, I threw away everything else, all of them will capsize. And the way that the capsize happens is always very comparable. So they always come from up here. They track this point, actually here, go close to this saddle point, and then fall down the other side. So the observation that we have here is that all transition events, in some sense, happen in a similar manner. Right? There is some kind of transition tube around the transitional region. Here, everything is drawn out by the noisy fluctuations around the fixed point. But in the transitional region, there is a tube through which all of the transitions happen. So for this capsize, yeah, go on. Yes.
I'm sorry. I guess naively I would expect some kind of symmetry here between phi dot positive and negative. So is there a reason that the capsize events happen to prefer rolling in one direction versus the other?
So there is a symmetry in the sense that you could go in this direction. Yeah, I'm just looking for a capsize to the right.
Okay.
So yes, it is obviously symmetric. What is not symmetric is that this well and this well have different depth, because upright and capsize, the potential is not symmetric with phi, but left and right is symmetric. I mean, that would be an ugly ship. I don't know, maybe some are, but yeah. Here clearly left and right are symmetric, and whenever it happened to the left, I just flipped it to the right in order to get better statistics and to have, I mean, it would be a confusing plot otherwise. Yeah, right. So the point I'm trying to make is that there is maybe something in there where I'm saying I could maybe describe this in a simpler manner, right? Instead of sampling, there is something underlying here that is typical for the ray event. So these events are rare. Out of the many simulations I have, only a small fraction of them do transition, but if they do so in a similar manner. And of course, I might also ask about the timescales that this happens with and so on. Right. So here's a more complicated example, but it is in the same spirit. So this is a simulation of the climate of Earth with what a climate scientist would call an intermediate scale climate model. So this is all of Earth with continents resolved, but you see already that it's quite blocky. So you have resolve your atmosphere with a few grid points, and the grid points are rather large. You have continents, you have water, you have ice shelves and everything. So you can plot the wind field. And if you let this run for a long time, it looks a bit like Earth climate. You have like strong westerlies, you have jet stream, and you have realistic looking temperatures and seasonal changes and so on. So intermediate complexity, because this has maybe roughly 10 to the 5 degrees of freedom. If you count everything up, there's pressure and wind mostly, but you have stuff that concerns the ocean and stuff that concerns the ice sheet as well and so on. And 10 to the 5 is not so, I mean, it's much if you consider it as, okay, I want to solve a 10 to the 5 dimensional problem, but this is small enough that you can run it on a laptop as well. You can actually download the code and do nice long-term experiments. So the observation that the corresponding PhD student did when he let this simulation run for very long times with a fluctuating solar constant, where this is just the energy input from the sun, and maybe you can argue that due to, I don't know, volcano eruptions or something, sometimes the solar constant is lower, and because there will be less influx of solar heat because of reflection. If you let this run for a long time, you will not necessarily stay in the nice climate that we are in, but there is a different state, and this is how it looks like. There is another state that you can fall into where all of Earth is covered in ice. So maybe you've heard about that. This is, I mean, I think it has made rounds, not necessarily this paper, but the whole observation in popular media as well. This is the snowball Earth state. And it is believed that Earth was in this state for a while, a long time ago. But these climate simulations, even though they are rather simple, replicate that. Even simpler climate models replicate that. Because the intuition behind it is rather simple. You say, if all of Earth is covered in ice, it is very white. And if it's very white, it will reflect a lot of sunlight back into space. So it will remain cold. So if you're covered in ice, there is a feedback loop that means that you remain cold and then you remain covered in ice. While the happy state that we are in, ocean is rather dark, so incoming sunlight will heat up Earth more and the ocean will stay melted. But both of these states are viable. If you think about this in some kind of molecular dynamics, maybe intuition, you have two wells and rare fluctuations might drive you from one well to the other, and they have in the past. Of course, it's not that simple. There are many external factors and there is no equilibrium, and who really knows what happens how. But in this simple climate model, you really have a single set of parameters that allows you two stable fixed points. And you might ask questions about how long do you expect to wait? What is the fluctuations? How do transitions happen? How do they look like? Right. So this is what in this simple climate model you can at least statistically answer, because you do observe a few transitions even without being very smart about it, just by waiting long enough. And here is what I want to show in this connection. So we project these 10 to the 5 degrees of freedom down to 2. There is the mean surface temperature. That's just taking the temperature of Earth at every point and average it. And then there's the equator pole temperature difference, meaning this is just because probably in this variable the states look distinguished, because if you have ice everywhere or not, this will make a difference. And then you can just plot in this 2D projected plane the whole distribution of everything that you observed. And here's how it looks like. So this is the mean surface temperature, and the purple dot is present day climate, and the dark one is snowball Earth. And you see these basins around it, if you interpret it as such, which is maybe a risky thing to do, but in this projection you see this basin and that basin, which are states that are somehow fluctuating either around the snowball Earth state or around the hot Earth state. But I promised you transitions, so you can do that as well, and the few transitions that we observed you can average, and you see here the average trajectory of how you transition from snowball to warm. This is the red line. So you climb up here and then you do a short dip and then jump quickly up and then fall back down here, while the backward transition, warm to snowball, looks very different. You have a very short, a very slow transient up to here and then you fall down there. So this is a bit maybe hard to interpret, even though I guess in the paper it was tried, it has to do with how different timescales behave in Earth's system in terms of how quickly it takes a long time for all of Earth to freeze over, right? So there are, while other things in this system are much faster regarding that. So we again observe, though, that these transitions always happen in a similar manner. So this is all stochastically forced. In principle, the system is allowed to do everything, but of course the physics are very constraining in that you can't do everything. It would be extremely unlikely to do anything but these transitions. So if I condition on the transition, I have more or less figured out how the transition must happen. There is not many other ways that it can come to be. Maybe the other remark is that forward and backward are completely different processes. So you have a most likely channel to go from warm to snowball, and you have a most likely channel to go from snowball to warm. Both of them are small transition tubes, but they are very different ones. So even this crossing point is just a crossing point in the 2D projection, of course. It's not obvious that there is maybe an underlying saddle point that you go through or something like that. Right. The last one is road waves. So this is quite a fun system that I spend a bit of time on working on, and the story is, I think, also quite entertaining in the sense that, I mean, entertaining, it's also dangerous, of course, but it's entertaining in the sense that there always have been tales of, I mean, humanity went to sea for a very long time, right? Longer than written history, and there always have been tales of extremely large waves hitting ships and drowning sailors and so on. And then I guess once science became a bit more rigorous, people started thinking about, oh, is this truly happening or not? Because, I mean, they are very rare. So you just think maybe the ocean has waves on it, and to a good approximation is maybe linear. So you just do a linear superposition of waves of a different amplitude. You can compute probabilities of observing a wave of maybe 20 or 30 meter heights. And what comes out in such a simple linear approximation is astronomically low. You will never observe such a wave. So for a long time, it was just believed that these road waves were just tails. I mean, I guess they have tails from sea dragons as well, and tails from mermaids and whatever, so large waves, why not? But they can't happen. This is not realistic. This can't happen. And this only changed comparably recently, and just because people have cameras around and were able to record it, or scientific instruments in the sea. So this is one of the first photos of such a wave. This is a tanker in 1977. I think the article is from, but I think also the event is from. This is an oil tanker, and it's quite big. I think this deck here is orders of magnitude 10 meters above the sea surface. It would be calm. And you see this wave approaching that is tall enough to hit the bridge that this photo was taken from. So this is a 20 to 30 meter high wave that is really hitting this tanker. I mean, the tanker did survive, even though the bridge was destroyed, so it didn't sink, and therefore the photo survived. But this exactly was the problem. For a long time, it was not only believed that the probability is very low, but also usually when you encounter such a wave, you wouldn't survive to tell the tale. But with like steel hulls and larger ships, this is no longer true. Nowadays, a rogue wave is usually survivable. And even better, this was in 1995. This was the first ever recording of such a rogue wave by a scientific instrument. So this is done in the North Sea on an oil platform that's called the Draupner platform, hence the wave is called the Draupner wave, which just is an ocean platform, and they have like a downward pointing laser that just measures the distance to the ocean surface. And you see these waves going up and down. So this is a time series in seconds versus the ocean surface elevation in meters. You see these oscillations, which are just regular waves. You notice maybe also that regular wave is still rather big because this is 10 meters. So that's maybe 5 meters top to bottom. So these waves are already quite large. But then you have this very isolated and very singular event that's so much bigger than everything around it that if you would fit Gaussian statistics around this would be just unimaginably small. I mean, here you see red line is mean and red strip is plus minus 1 standard deviation. So this is 3 or 4 standard deviations or so. So we naively think this is impossible. So this was a wave crest to trough of 25, 26 meters, which is also extremely big. So I think it is still fair to say that the mechanism of the creation of rogue waves is still not fully understood. Of course, a lot of people have a lot of theories, and maybe this is more a question on defining exactly what you mean with a rogue wave and what you mean with the mechanism. But there is a lot of debate on what really causes this. But there is the general belief that there is some kind of nonlinear effect going on. It's not as simple as just small waves linearly superposing, but some kind of modulation instability and so on. This is not important here, of course. But maybe what is important is that the probability density of the ocean surface elevation in the tail is unknown and would be very helpful in order to estimate the risk of encountering such a wave. So in some sense, you can say this is a sampling problem. I'm interested in the probability density of the ocean surface elevation under certain conditions. Of course, all of this depends on the conditions, how strong is the wind and so on. Unfortunately, the ocean has a rather long memory, so you can encounter very high waves, even in very quiet sea, because wind or storm might generate waves hundreds of kilometers away, and they remain large for a very long time. So you encounter a large wave, might not mean that you are currently in a storm. It might just mean that a storm happened elsewhere a long time. So the goal would maybe be to estimate the tails of this distribution in some way. And I'm saying this was a fun project because this is the first and probably the only time I got to play with experimentalists. They are able to record these things in a proper experiment. And the data sequences that they observe are again of this form. So this looks like the Doppler wave signal, just that this is coming from the experiment where you have time in seconds versus elevation in meters. You can see that this is much less impressive because the elevation in meters goes to 0.2, which is 20 centimeters. But as usual in fluid dynamics, and this is also true here, everything is in some sense scale invariant, similar to how you can scale down an airplane model to something smaller and have a small wind tunnel. You can scale your ocean down and you still have the same physics to some degree. As long as you're not running into surface tension effects, which here are already negligible, it's the same physics. It's the same equation. If you non-dimensionalize everything, you don't care whether this is 10 centimeters or 10 meters. Right. So the terminology that is there used is then eta is the surface elevation. So you have surface elevation in meters against time in seconds. And you define something that's called the significant wave height as 4 times the standard deviation of eta. So that's what I plotted here. It's called significant wave height because, I mean, I guess that's maritime engineering for you because this is the height of a significant wave. So here are a few waves that you would call significant and they are roughly of that size. And then you define a rogue wave, that's the proper modern definition of it, to be twice that. So this is the rogue wave threshold. And here I picked a signal where you have a rogue wave. So you see that this is 4 standard deviations, so this is 8 standard deviations, so this is a ray event, in a sense. Right. Experiment and look. Oh, yeah.
So what's H is like twice the wave. H is 1 standard.
Yeah, sorry, I didn't say that the significant wave height is called HS. Right, HS is 4 times standard deviation of this signal. And then twice that is what you would call a rogue wave. So a significant wave is already a big one. I guess significant means it's something to consider, but a rogue wave is twice as big. So here's how the experiment looked like. There is a very long wave channel, so 240 meters maybe, and then it ends in some kind of beach that's shaped exactly like a square root function, because that somehow dampens the reflections in an optimal way, because you want to create waves on this side, and you don't want reflections happening back into the channel. And on one end, you have a wave maker. So it's 10 meters wide, but on this scale, 10 meters is basically one-dimensional, and you want to have your waves one-dimensional. So you have a single wave maker. And this wave maker rocks back and forth, I think, to produce waves that are realistically looking. So there's a random signal that's fed to the actuators of this wave maker that push it backward and forward, and then you have wave trains traveling down here and deforming by whatever is the equation that determines the surface elevation of the water, and then they run to the beach and then they get destroyed. These waves are planar, and that's a rather good approximation, and they checked so that it's really a one-dimensional problem in this sense. And in the experiment, there were like 19 probes located along the wave channel where you have one of such signal that I showed you, and then they just record days and days of data where you just randomly push it and then you observe the waves. So of course the question is, what do you feed in? And that's makes everything very different. If you push hard, you get higher waves. If you push weaker, you get lower waves. And exactly how you should push, like what should be the statistics, is maybe a good question. But there is an agreed way of generating waves, because there has been already half a century ago, I think, a very big experimental project that just measures the energy spectrum of the ocean under certain wind conditions. That's called the John Swap spectrum. I think NS in it stands for North Sea. I'm not so sure, but I think it's Joint Observational North Sea Wave Amplitude Program or something. So they put a lot of probes in the North Sea and they measure what's the energy distribution in terms of frequency versus wave spectral density. And this you can do for different conditions. And in the end, they have two parameters that they care about, the significant wave height and the fetch, I think, or two maritime parameters that I don't really understand. But you can, if you consider the non-dimensional system, basically can reduce it to the significant wave height that we've seen, which is just how high are the waves, and another parameter that basically tells you how nonlinear is the system, which maybe makes sense. You have a wave equation that has nonlinearity, and whether or not this nonlinearity is strong or not depends on how high your waves are and some other factor that somehow has to do with the signal that you feed in. So this is the signal that they feed in, and then arguing that this is a typical ocean, you can just say this or that are my ocean conditions. Everything is parameterized by this, and then I can record how these rogue waves look like. So what you get then are signals of this form. Again, against time, I have elevation eta, but now I have probes located along this wave tunnel, along this wave flume, if you want. For example, one at 10 meters, one at 30 meters, one at 40 meters, which record a time signal. But because you know everything about the system, including the group velocity of the waves that travel along it, you can identify. So this is in particular the thing that then was done as statistics, is you define yourself an endpoint, in this case 50 meters. You have your threshold, for example, the rogue wave threshold or something higher. And whenever you identify a wave that is high enough that it qualifies to be a rogue wave, you look at this wave package, but I also know where this wave package was earlier, at the earlier probes, and I take a wave package there as well. So I not only get statistics about how do typical rogue waves look like, but I also get statistics about how do typical precursor events of rogue wave events look like, because this speed is known. And this is what you see on the right, exactly on this data, where this is the typical 20 centimeter high rogue wave event, just the experimental mean and plus minus 1 standard deviation at the final probe. I guess it's 45, not 50 meters. And then at the 30 meter probe and at the 10 meter probe, you see. So what you again see is that around the event, the standard deviation is actually quite small. And all of these rogue wave events happen very much alike. You have, just by conditioning on this fact point, something that's very similarly looking, not only in space, but also in time. And every time I observe such a rogue wave, to a good accuracy, it's very similarly looking to all others that I observed earlier. So they happen in a very predictable form again. So they are rare as well. Out of this very long data set, there are only a few that qualify, but all of them, even though they are just a few, they all look very similar. Right. So this is the observation that I want to do. Rare events are often very relevant in real-world systems, and what I've just shown you is a few examples of, for very, very different systems, but every time some rare event happening, they often happen in a similar way around a typical transition tube. So here is the same thing for the ship capsize problem or an oscillator problem, where I say there is always this tube, and then I have painted this white line that somehow lies at the center of the tube. And the hope is that I can compute this line instead of doing all of the sampling. This is what all of this will revolve around. Right. So there are many questions associated with it. Maybe most relevant is how often do these transitions happen? So what's the transition probability, or maybe what's the mean waiting time to observe such a transition? And if they happen, in what way do they occur? Because I have this information about the transition tube, I can not only talk about probabilities, but I can actually look at mechanisms if you want, right? I can tell you, okay, if Earth freezes over, this is how, and this is not how. And in particular, and if you want to prevent them, you know what channel you should address, right? There is maybe mechanisms that are necessary for this to happen, and you can block them. So these are all probabilistic questions, mean first passage times or hitting probabilities, but because the systems are rather complex, we can only answer them numerically. All right. So I want to make one additional point just to connect a bit to what we've seen. All of these examples are rare events, but in some sense, they were not all of the same type. Two of them that I showed, all of them in my simple mind, are examples of stochastic differential equations, right? Maybe the space is rather high, it's all of Earth in B, like this B does a lot of heavy lifting, it describes the ocean and the atmosphere and the ice sheets and so on, and there is stochasticity on top of it. But this is the equation that I consider. But the two of them were of the metastable kind. Metastability in the same sense as we've seen for maybe polymer chains or something like that. I have a typical state A, this is the warm Earth, or this is the upright chip. And I have another state B that is also viable. If I would be in the vicinity of it, I would stay here. So the streamlines here are supposed to be this vector field B. And wherever I start, I will very quickly either go to A or go to B. But once I am in A or in B, as long as epsilon is small, and that's the assumption here that these things become rare, I will stay for very, very long time scales, either confined to A or confined to B. And it will be very, very unlikely for me to explore the other state. So the transition event from A to B and also from B to A back is very rare, while the mixing time individually in A or in B is comparably short. It might still be long. In Earth climate, there are very long time scales, but A to B, snowball to warm, is extremely long time scales, of course, that you need to wait for this to randomly happen. I guess it will never randomly happen. But one of the examples, namely the rogue wave example, the rogue wave is not a stable state, right? It's just transient. I can maybe build it up with noise or with whatever, but then it will just decay again. This is what I call an extreme event. I still have a typical state where I spend most of my time in, and I have another set that is not distinguished in any way, except this is what I care about. So I define myself another set. That's the one that is relevant to me. And then I just ask about the probability of transitioning from A to B again, just now that if I would hit B, it would only be in a transient manner. So in some sense, if you view it like this, it is not very different. It's just a question of whether the target set is like also something stable or not. In terms of methods, it sometimes makes a difference and sometimes not. So we will see. But I just want to observe that these are the two flavors that we go about. So here I would have multimodal stationary distribution that I would want to sample, and that's a known sampling problem. Here I would want to sample tails of a distribution, which is similarly problematic, but slightly different in nature. And the question we are aiming for is how we compute these probabilities, in particular in the small noise limit. So if this would be inverse temperature, then a very cold chemical system has a very low probability of transitioning. All right, so maybe as a last remark, maybe that's obvious to anyone here, sampling here is very hard because the events are very rare, but maybe more precisely, for example, if the transition probability follows some Arrhenius law where you have to climb up an energy barrier and fall down the other side, and I take a naive sampler that's just averaging on the indicator that the event is happening. So I mean, I guess xi is my ith sample, and then this is just 1 or 0 or 1, depending on whether or not I have a transition. Then the relative error, which is the square root of the variance divided by the expectation, scales like 1 over square root of n times p, where n is the number of samples and p is the probability of the event. So this is just, I guess, it can either be 0 or 1, and it's a very low probability of observing a 1. So I can just reduce this known quantity to this approximation. So if p is exponentially small in beta, the numbers of samples that I need in order to get the constant error for sampling this is exponentially large. So this is the fundamental problem that I encounter here. I have an event so exponentially rare, and I conclude from that that if I want to still sample it with a good accuracy, it's not enough to observe it once because my variance will be orders of magnitude larger than my mean for any observable that I define myself over such transition events. I need to have an exponential number of samples to get the number of, the relative error to be small. So in some sense, this is the fundamental problem of rare events. Of course, you can also say there is more distinctions to what we've seen, I guess, this week most of the time, because in many cases, I'm not really interested in drawing from the invariant distribution, right? Like, if I would ask for the ship capsize problem, is it more likely for the ship to be in the upright state or in the capsize state? The answer is probably going to be for the invariant distribution that the capsize state is more stable. Once I've capsized, it's even less likely that I uncapsize due to random waves. The capsize state is deeper. But I mean, if you just look at a random ship, it will not be capsized because we're not starting from equilibrium if you're looking at ships, right? So I'm interested not really in drawing randomly from the distribution of ships from equilibrium, but instead I'm interested in asking, given that the ship is in this state, how likely is it to go to this other state? So maybe also because many of these observables will actually be depending on dynamics, that's also different, and that was my confusion in many of the questions that I asked. I care about how long does it take. I care about the underlying physical system. My Markov process that is underlying this is not just a tool to sample the distribution, it's a physical process, and I care about what it's doing. And even though I am maybe allowed to manipulate it in the importance sampling sense, I should keep that in mind whenever I interpret the results, right? And if you want to do this in an unbiased way, this is very difficult. Or maybe phrase this in another way, maybe my systems are very high dimensional, but what I actually care about is maybe the ensemble of transition paths, which is an even higher dimensional space, right? Even for a small system like the capsize problem, just two-dimensional, transition paths are still a function space, or if I discretize them, still 100 or 1,000 dimensional space. Right. So this is why I segue into large deviation theory is maybe the answer to some of these things, or at least underlying the intuition between many of the observations that we've made. So the idea behind large deviation theory is, in principle, to skip sampling completely. And instead, what we want to do is to compute the most likely ray event only. So I don't draw any random samples. Instead, I solve some kind of optimization problem, looking at the most likely one only, that is somehow lying at the center of this transition tube. So I observe this transition tube in many systems, and I'm saying I am, in principle, able to compute where this is lying. And if I would, then I would be able to talk about ray event probabilities even in a very small noise limit, because I have this prototypical event instead. So what I'm doing is replacing an extremely complicated sampling problem with an arguably still very complicated optimization problem, which I need to solve once. I always get the same answer, and hopefully this answer is in some sense correct. And it's provably correct in a rigorous way for a large class of systems. This is what we're going to deal with. Right. So I think this is somewhat, I mean, who here knows about large deviation theory? Ah, perfect. One. So, I mean, my assumption was that people don't, and I guess this assumption is almost true. And I wanted to highlight this from a few different angles. And then when I thought about what to talk about precisely, there are many different angles that you can think about. I mean, here's what I came up with, and this is in some sense the outline of what's going to happen. There is the probabilists approach. This is just defining what is large deviation theory as a mathematical theorem and when does it apply and so on. This is maybe not very helpful in understanding what's going on, but it's maybe helpful in understanding what's the rigorous results that you can rely on, as opposed to what is just intuition that is not necessarily true in all systems and so on. But then I have like a list of, I guess, other fields' approaches. I felt like, I guess, if I'm stepping on someone's toes, I might as well step on everyone's toes. What I call the chemist's approach, which maybe is insulting to the chemists, something like Arrhenius law and Irene Kramer's formula. There is the so-called string method that's very similar in spirit, if you've heard of that. And this is what we will address first after I got to the mathematical foundations. Then something that I would call the physicist's approach, even arguably many of these things are physical, which relies on path integrals and stochastic field theory. And maybe you've seen a bit on this on Tuesday. Unfortunately, I couldn't be there for the QCD lecture, but I mean, I can't think that you can do QCD without path integrals, or did you?
Yeah, we did effectively with path integrals. Yeah.
Right, okay. Then there is the engineer's approach. There is something that's called first order reliability method. That's, I guess, also a stats thing. Who has heard of that? So maybe it's the engineering approach with the reason. This is like reliability engineering still cares about probabilities, and in particular about rare probabilities of having a reliable system that then fails. And this is closely connected in some sense to what we are doing, at least to a special case. And the last one is probably the worst named one, computer science's approach, but it's the numerics approach in terms of there is a perspective on this coming from optimal control and numerical optimization, where you can do a lot of things. You might also notice that this list is lacking the statistician's approach, and we are in the statistics building. So I think there is also statisticians' view on this, which is related to maximum a posteriori estimates, which I don't know much about. So maybe someone else can jump in and tell me how this is exactly what I've been telling you all along and how this has already been discovered 100 years ago in stats as well. Because of course, all of these approaches are not very new. So this is the rough line out. And what I intend to do is I basically use these to give different intuitions of the same thing. So hopefully this is not too slow and too boring. But I think if I would only give you the, okay, here's the theorem, that's what you do, it will not be very illuminating. And some of these actually give you a perspective that's hopefully helpful, even though you are not an engineer or not a physicist, or maybe you don't care too much about numerical optimization. Maybe some of them are not so helpful either. We will see. And then each of these will, I guess, equip me with notation to address yet a different problem. Because some of them are necessary, like some of these problems you cannot do without sophisticated numerical optimization techniques, for example. And some of them are of a different form so that you can use different notation to address them. But they will all be large deviation problems that you can solve, and I try to like distribute application examples throughout. Are there any questions so far? There are not? Yeah.
Path control, so this stuff is actually sum over different paths. It's an integral over different paths. Whereas here you're talking about like finding the most likely path.
Right, but I mean, it is what I'm going through. In between, I am talking about a sum over different paths, and then I'm neglecting all but one. Right? I mean, yeah. With path integral, I mean, we will spend a while on that, I guess. But I'm not sure it's very deep. At least I will not go very deep because I can't go very deep. Maybe this is also a good point to make a first break, because then we will jump into the actual content of all of this. So maybe 10 minutes and then 10?
Yep.
I think I'll go get a coffee.
Mauro asked me to give you the
If you want to enter the benches before you get,
Is it not a gift?
if you want to leave it, you can leave it. Maybe the math.
Definitely not the physics.
No.
Very good. I mean, but understanding the theory works in automatic. So if we got two coordinates for next one, next two, some points to condition for next one. You've got the score of the joint, and the sample condition will just have to be this one, and then you run the SD.
Yeah, you have to go think about that. You have to think about how each concept.
Yes.
And that's how you do.
Yeah, no, I mean, it's very simple, but then, you know, theory.
I think in practice, if they don't decide what you actually get to get it done, you get some response.
I just got a few terms. I mean, I think it's drinkable.
On y va maintenant. On y va maintenant.
Yeah, sure.
Parce que mais la France a posé le train à 15h05 à
Pourquoi tu mets le train de
la avion à la laisse qui demandait. Et en fait, il y avait un problème sur le retour, dans le sens où je devais réserver le retour exactement. Non, c'est moi qui l'ai choisi, mais j'ai pu le prendre directement sur site. Mais le retour, je ne
I'm curious whether you have a chance to follow up on this short number of steps question.
les trains de fond, les lignes.
Je crois que j'avais mis quand même
So what you need to be true, I guess, somehow is A over K plus 1 factor is still correct.
Yeah, the thing is that something is actually not get right master. So this is not time of doing something around the
Okay, so you may, but maybe you're still happy with a 5 or 6 and Sure. Actually, do you know where that is from? Actually, anyway, thanks.
Yeah, sure. I've been drinking for hours on this now for an hour, so yeah. I mean, talking out here.
Shall we say we talk from one to in a way, once you, in some settings, the idea of having a most likely cost.
Basically, the thing is like, let's say in that assembly you have of iteration, right? So at iteration k, you have some particle, and then you have iteration k plus 1. So basically what is happening, let's say you have 5 particles, 1, 2, 3, 4, 5, iteration k. And what you do is you choose the one with like lowest highest energy.
Highest energy.
In a sense 5. You kill it, then you take like 3, and you move to some kind of frequency.
Yep.
So you get some kind of pi, and then you iterate up. So the question is why if I only do like a small number of things instead of solution? Because normally you would like 3 and 5 to be correlated, right? And so you need really long iteration. What happens is that even if they are not really correlated, like you only do one step, okay? What can happen is even after that, in subsequent steps, maybe 5 would be applied on by some other system.
Yeah.
So if you have a lot of intermediate iteration, or even some iteration do a lot of steps, it could be that many of the steps finally will be applied to the
But it wouldn't be 5 prime, I guess, the next MCMC step, right? It would be the duplicate that produces a new particle that gets the next step.
But if you look at like the general, same thing. I mean, the next step will be something like something else. And if you have a lot of them, then eventually you come back to 5 prime. Eventually, you have to be refreshed by another.
Right.
So even if you even a single iteration before small number of steps, at the very end you have a lot of units. You can add up a lot of energies and
So let me take the limit of this approach for a second. What if I do 0 MCMC steps? So I delete the highest energy point and I just duplicate randomly one of my lower energy points. This definitely is important. So somehow it's important, I guess, that your number of MCMC steps total is scaling also with the number of iterations.
that was a
key point. So you have some number of particles and you have many more iterations than the number of particles. And then your MCMC steps somehow is fixed in the number of iterations. So this is why it says for 5 particles you can choose 1 iteration, for 4 particles 4 or 5 iterations.
So basically what happens is
yeah, you'll end up with some kind of cluster around some maybe root ancestor particle, right? On average, be a good number of MCMC steps.
Yeah, that would be great.
Yeah, it's fine.
All right, so let's continue. And as I said, I would start with the mappy bit to get this one out of the way, and it's probably maybe the right order just so that we have our terminology in place that we can then later like soften up and interpret and make more intuitive. So here is the definition of a large deviation principle, and that's the relation to large deviation theory is that some random variable fulfills a large deviation principle. So I have a family of random variables xn indexed by some integer, and I care about the probability that xn is in some set A. And we say that this probability satisfies a large deviation principle with a rate IA indexed in A. If this is true, that the limit of n to infinity in this family of -1 over n log of the probability is equal to IA. So this is just the bare definition, and I just throw this at you without any introduction or anything else. but that's just how we define it for an arbitrary random variable. And it looks rather specific, right? This is like, if this limit exists, I guess it's finite, otherwise it doesn't make much sense. Like, why would a probability fulfill this necessarily? It's not quite obvious that this is relevant to anything. The way that I often abbreviate it, or maybe that it is often abbreviated, but in particular in this talk, is that I just solve for the probability instead, because that's what we care about in some intuitive sense. So I say the probability that this random variable is in some small slice ds scales like e2 minus n times is ds. So I'm saying the probability in some interpretation of scales like behaves like an exponential distribution, and I know the rate of the exponential decay with n to infinity. So the event itself is somehow parameterized by this s, and the rate function is only a function of s, and all of the n dependence of this limit is in this prefactor. So I'm saying a large deviation principle means that the exponential tail behavior in the n to infinity limit is known, and this is the scaling. It's e to the minus n. And the precise definition of scales like is that I'm saying that it's log asymptotic equivalent. So the logs of the two series have the same limit if I appropriately rescale them. But the intuition really is that in the tail, in the large n limit, it will exponentially decay, and the rate of exponential decay is given by the rate function, or the rate IA, and that's why it's called rate function. That's the rate of the exponential decay. So as I said, it's maybe not at all obvious that this is relevant for anything, but okay, you can define it, and that's all good. Right. So maybe a very, very simple example that would be very natural is I just have IID Gaussian randomly distributed random variables. So xi is normally distributed with mean mu and variance sigma squared, and I want to consider the sample mean. So 1 over n of the sum of all of the xi's. So if you've done probability A, this is what it's called here, I think, or maybe probability 1, the undergraduate lecture, you will have heard of the law of large number, and this is how you would call it. It's a limiting law for probabilities, where I'm saying the limit of n to infinity of the probability of this sample mean to lie in some area around the mean is equal to 1. If I let n go large enough, with probability 1, I will be as close as I want to the actual mean. Right? I guess like Monte Carlo samplers rely on that in some sense. But this is just the first in, I guess, the standard trifecta of limiting laws for probabilities of random variables. So in this case, for the Gaussian random variables. And the second one that you usually encounter is the central limit theorem. This is no longer saying on how the mean behaves, but this is telling you how fluctuations behave. But it's maybe more precise than that. It's telling you how typical fluctuations behave. So here I'm saying I know what the mean does. Here I'm saying, yes, I know what the mean does, but the sample mean is a random variable. It's not a number, it's a random variable. How does it fluctuate around the mean? Well, with n to infinity, square root of n times the difference between my sample mean and the actual mean is Gaussian distributed as n to infinity. Or in other words, if you do it in an intuitive way, a typical fluctuation is expected to be order squared n as n to infinity. So the last one in this trifecta is the large deviation principle, which is fulfilled for this sample mean for Gaussian random variables and many other things as well. And here the question is not what typical fluctuations look like, but instead, how do order 1 fluctuations look like in the n to infinity limit? So these fluctuations become smaller and smaller as n to infinity. I mean, I have fluctuations of order 1 over squared n if you phrase it like that, right? But here I'm postulating that I want to keep a finite and n-independent fluctuation away from the mean, and I look at the probability of this happening as n goes to infinity. And then, I mean, that's obviously true for Gaussian random variables and sample mean, that the sample mean is in any s or s plus ds, scales exactly like this large deviation law that we have, and the rate function is given by this Gaussian, because the tails are just Gaussian. That's obvious, right? There's this n scaling as I let n go to infinity. So there's no surprises here because it's just a Gaussian distribution. So these are usually the three things that you can do. What's the typical behavior? What's the typical behavior away from the typical behavior? And what's the atypical behavior away from the typical behavior? So no fluctuations, small fluctuations, and large fluctuations. Or expected fluctuations and unexpectedly large fluctuations. That would be what the large deviation principle covers. So as I said, it's maybe not quite clear where this applies and how this applies, but there is a series of theorems that cover proofs on when a large deviation principle exists and for what random variables it does, and I will cover them. I think the remark here is that these kinds of problems came first up in, I guess, insurance mathematics, and that's where large deviation theory has its origins, in that I care about, for example, default probabilities if I'm giving out loans or something like that, which are very rare, but then I care about a single one of them failing, and then you get statistics of this. Here's what we need to define next in order to generally tell you at least a large class of random variables fulfilling a large deviation principle. If I have a family of random variables, as I now postulate I often have, parameterized by some n, I define a scaled cumulant generating function. So maybe you've heard of the moment generating function, maybe you've heard of a cumulant generating function, and this is then also properly rescaled with 1 over n, and it's called scaled cumulant generating function. So this is a function of some parameter lambda, and its limit of n to infinity 1 over n, and then log expectation exponential, which maybe a lot of people here have already seen multiple times with free energy and so on. And I guess there is a very deep and rigorous connection between equilibrium statistical mechanics and large deviation theory, and these kinds of things are at the very foundation of that. So I have e to the n, then I take the expectation, the log, and then I normalize with the n again, and then take the n to infinity limit, and all of that is a function of lambda. So fair enough, this is just a thing that you can define. And then the theorem that I want to highlight here, I mean, there are many similar ones, but this one is covers a large class of random variables. It's just saying if this function exists and is differentiable, then I have a large deviation principle. And not only do I have a large deviation principle, but I can write down the rate function. And the rate function is nothing but the Legendre transform, or the Fenchel Legendre transform of the scaled cumulant generating function. And I think, I'm not precisely sure, but I think there is some kind of free energy, entropy, blah, blah, blah thing that exactly happens in the same way in StatMech, right? I mean, maybe someone can illuminate that, but I mean, this is the mathy version of the probability theory version of this, but you encounter such Fenchel Legendre transforms in statistical mechanics as well, right? And I think it's the same basic idea that you can then prove these exponential bounds just given this scaled cumulant generating function. So maybe none of this is very intuitive, that's what I warned you earlier, but this covers already a very large class of random variables, and it's actually not so rare, I guess, for a random variable to fulfill such a principle, because this is rather ubiquitous. And then maybe the last theorem that I want to highlight is the so-called contraction principle, and that's just saying if I have a random variable an that satisfies a large deviation principle with ia, and I have a continuous function h that maps to a new random variable, and continuous is the only thing that I need, then this new random variable also satisfies a large deviation principle. So if I have one, then I can construct many of them. And I can also write down the rate function. The rate function is just the infimum over isosets of h. So if there's multiple a's that realize the same b, then I take the smallest one. And that's maybe intuitive because I have this exponential decay of probability, so all that I care about is the smallest one, because all others will be subdominant in e to the minus a. So maybe let me repeat that because it maybe wasn't so clear. The large deviation principle always is of the form e to the minus n rate function. So if I map this through and this map is not one-to-one, then I have maybe multiple a's that map to the same b. So if I care about the rate function in b, the only thing that survives here is the rate function of the original one, that is for the minimal I, because all bigger i's are already exponentially smaller than this one in the n to infinity limit. So it's only the infimum that I care. Right. So, I mean, I guess I warned you, but you do notice that there is quite the discrepancy between all the lofty rogue waves and climate stuff that I talked about, and then this one here. Like, what does this have to do with anything, right? I mean, what's the random variable and so on? So the connection, and that's the title of the whole morning, is that I don't necessarily care about large deviation principles for any random variable. I care about large deviation principles for sample paths. So I have an SDE, and I'm interested in large deviation principles not for some specific random variable, maybe Gaussian random process, but for a whole path. So I want to do the same, but starting from an SDE. So these are the SDEs that I always claimed are maybe underlying any of these systems. Maybe the B is rather complicated because it encodes all of planet Earth, but I mean, in principle, it's of this form, hopefully. Can we say anything about the probability of any sample path being close to a given path? So it's the same idea that I'm saying there is hopefully some exponential decay of probability, but now in path space, if you want. And the intuition is as follows. All of this relies on Brownian motion. And if you squint, then Brownian motion is something like the continuum limit of the sample mean. I'm just adding up lots of Gaussian increments and then doing infinitely many of them. But in the end, all I care about is the sum of all of these Gaussian increments. And we already saw, like, as the easiest example, the sample mean of Gaussian random variables. So maybe you can hope that at least the Brownian motion itself falls into a similar class because it's the sum of many individual Brownian increments. And this intuition is indeed true. And the corresponding theorem is called Schilder's theorem. So I have a scaled Brownian motion. So Wt would be Brownian motion, but Wt epsilon is square root of epsilon Wt, and Wt is the usual one. And then the measure for the scaled Brownian motion also fulfills the large deviation principle with a rate functional, so no longer a rate function because I'm in some trajectory space now, where j, which is the rate functional of some trajectory phi, is equal to some integral of phi dot squared. So I thought about whether I should make this more intuitive at this point, because you can argue this through Gardner-Ellis with some hand waving, the way that we could do for Gaussian random variables, where you're just saying, okay, the probability of Gaussian random variable is e to the minus x squared over variance, and if you have many, then it's the sum, and if you have continuously many, it's an integral, and that's exactly what happens here. But I don't think it's very illuminating at this point, but it's true. Probably true.
So here the large deviation principle is for W capital T epsilon, right? Not small t.
So it is not. This is truly in path space. My intuition argument was for that. But the large deviation principle is truly for the path.
Okay.
Yeah, so maybe that was misleading, but the intuition is still valid and I can do this to any t.
Okay.
So it's true for every t, and then I can do this in path space. So this is maybe also not very helpful, but then it's a very... Oh, yeah, sorry.
Yeah, so that lab deviation is with respect to which path, which reference path for that deviation.
So what exactly do we mean with reference paths?
Because like whenever you have, okay, so for instance, in the last deviations stuff for the mean, you are looking for deviations with respect to the mean. So here, what's the deviation with respect to some path?
So I can pick any path, phi. I can tell you that, I mean, the probability of observing this path decays exponentially, and the rate of decay is this function that I can apply to this path. Does this not answer the question?
Yes,
Any path.
So the probability that Wt epsilon is actually equal.
Yeah, I mean, it's more precise, and I will make it a bit more precise, but it's like being in a dot cube for any dot bigger than 0 or something like that. Right, so I can take this result and now go to the full final thing that I want to do. If I now have a stochastic differential equation, this is slightly more generic than the one that I had before, because I have a covariance matrix in front of the noise. Then I can say the sample path of this one also satisfies a large deviation principle with this rate function. So this is now what I call S of phi, or rate functional. And it's this somewhat ugly function formula. Phi dot minus b times a to the minus 1 as a function of phi times phi dot minus b again, where a is the noise covariance matrix, so sigma, sigma transpose, where this is the sigma in front of the Brownian motion. So why is this true? With the stuff that I said, it's already, you can already anticipate. This is simply because the map from Brownian motion to the solutions of this SDE is continuous, and then you can do contraction principle. If I have a large deviation principle on the Brownian motion, I have one on any SDE. Given the map is continuous, which I guess is the same as asking whether the SDE is well posed, so you need Lipschitz or whatever. Yeah?
These are as epsilon goes to 0.
This is all in epsilon goes to 0, yes. Yes. Yeah, this is a good point because I switched very quickly from n to infinity to epsilon to 0. But epsilon takes the role of 1 over n here. That happened in Schilder somewhere because I was somehow arguing before about sample mean and I normalized with 1 over n, but the integral is no longer normalized, but of course it's multiplied with the 1 over epsilon, sorry, with the squared epsilon. Yeah, good question, sorry. Yeah, so Maybe it's not too helpful to do all of these things very quickly, but I'm also not sure whether it would be very helpful to go through all of the details. So here is maybe then the way to, this is the final result, and in some sense we are done. I now have shown you the rigorous result that says there are large deviation principles for a very large class of stochastic differential equations in the noise to zero limit, and this covers all of the cases I was talking about, right? I mean, if the noise is small, which is maybe not always, but that's the limit that we find ourselves in, because if I call my system deterministic, so my double well is just coming from the B, in order for the transition to be rare, I need the noise to be small. Yeah?
Is this true if you don't have a finite horizon as well?
In time?
Yeah.
Yes, something like this is also true on infinite time horizon. I mean, this theorem isn't, but yes, it's very regularly considered as well. And it's relevant for things like mean first passage times or. Yeah, I mean, here I'm asking about observing a certain path. So here's my words explanation for this, and this maybe addresses a bit also the reference. The probability that the sample path of my SDE is close to a given path phi of my choosing fulfills this, that for all delta bigger than 0, I guess small enough, this probability, which is a bit long, so let me unpack, supremum over t, meaning what's the largest of this argument, and that's just in some norm the difference between what I observe and what I want to observe. So the largest difference between what I observe and what I want to observe is bounded by delta, meaning I stay in a delta cube around phi. What's the probability of staying in a delta cube around phi for all times? Scales like an exponential, and in the exponent I have my smallest parameter to the -1. So I used to have minus n here, now I have minus epsilon to the -1 here, times this rate functional evaluated at phi. And that's true for any phi. And S is given by this, so I write it in a bit of a shorthand notation. It's basically phi dot minus b squared. I just redefined my inner product to be the A inner product because I had like an inner product here that is phi dot minus b squared in some A to the -1 norm. So that you can interpret the covariance matrix as some form of metric because it determines which directions you can easily fluctuate into and which ones you can't. So this is a very natural way of writing it. At least as long as A is invertible, which it maybe not necessarily always is. But yeah, it's this nice shorthand. So we have a rate function and we have these kind of things. What we actually care about is maybe transition probabilities and such things. So for example, the probability to transition from some point X to some point Y, we can then view as a minimization problem, namely the probability that xt at final time ends up in a delta ball around Y, given that I start at X, also scales like an exponential, where in the exponent, I only need to look at the minimizer of all of these rate functions over all trajectories that connect X to Y. So why is this true? I could give this the short answer and say this is yet another contraction principle, right? The map from the sample path to the final point is continuous, but it's also intuitive because I'm saying in order to get this probability of transitioning from X to Y, I can simply look at all of them. And I know for all of them that they scale like this. So in epsilon to 0, all of them will exponentially faster decay than the one with the minimal action because there's a minus here. It's the minimal one that matters. So I want to minimize the rate function over all paths that do what I want. So this is just an example for transitions from X to Y or from one set to another set. But that's true regardless of what I do with very little restrictions, where I just say the probability of my system doing whatever I want is the minimum of the rate functional over all trajectories that do this same thing. Right? It might be starting at a point and ending at a point, starting in a set and ending in a set, starting at a point and having a very high wave at the end, whatever that is, a set, I guess, right? But it's just a very, it's not an endpoint that I want to prescribe. I just want to have like a constraint on the endpoint maybe, and all of these things. You might even talk about like time integrated quantities or means and stuff. So this is what we are getting at. And in particular, we're interested in this minimizer, phi star, which is the argument of S. So I'm saying, I mean, I need to solve this minimization problem, but the path that then is the minimal path has a meaning, is the center of this transition tube, right? It's where I would concentrate on as I let my noise strengths go to 0, conditioning on the transitions to happen. So I want to solve this minimization problem of the rate functional over the space of, I guess, absolutely continuous trajectories that connect X to Y, for example, for the metastability problem.
That minimizes the transition tube that you have mentioned earlier?
It's in some sense at the center of the transition tube. Maybe more precisely, it is what the transition tube converges to in the epsilon to 0 limit. Because fluctuations around it become smaller and smaller as you let the noise go to 0. So I think, in other words, the only way that the ray event is allowed to survive, if I condition on this more and more ray event of transitioning from x to y, is this single trajectory. All others are exponentially suppressed. That's I think, the way of phrasing it. Right, so, I mean, not sure whether this was all helpful, but this is where we have arrived now. And that's maybe if you felt like you didn't get much from the mathy bits. This is maybe where we can all like reassemble and recollect what is now happening. We have one single main problem, and that is finding the minimizer phi star that minimizes the rate functional over all trajectories that do what I want. For example, transition from A to B, sorry for switching notation, where this is the set of trajectories that transition from A to B. And S of phi for this is given by phi dot minus B squared, if my sigma is identity. So this is for this particular system, x dot is equal to B plus noise, when I have white in time not. So if I would have that, then not only would I know something about the probability of the event, namely the probability of transitioning from A to B scales like an exponential, and in the exponent I have my smallest parameter and S at this minimizer, but I have this transition tube center itself. So I actually get this white line out of, and this is how I computed this white line. If I would let epsilon go to 0, this cloud of particles would concentrate on this white line. So this cloud is only big because my epsilon is non-zero. I need to have a finite epsilon to observe any transitions in reasonable time on my computer. But if I would wait longer and longer and longer and longer, this would shrink, and the thing that it would shrink to would be the white line. And of course, I can also interpret this as what's the corresponding force, the corresponding Brownian motion that pushed me over. So I can maybe invert this and say, I want this to happen. It's rare, but I want it to happen. How do I need to kick my system in the most effective way? Right. So first example of this, where everything can be done on paper. This is an Ornstein-Uhlenbeck process with a restoring scalar variable gamma and some small noise. And I want to consider the event that at final time t, which I guess is 10, or like from minus 10 to 0, so maybe 0, I exceed some threshold z, which here I pick to be 1. So I can write down the solution of this optimization problem on paper because it's not a very complicated one. Because it's this one, it's the minimizer of S of u, where u is in the space of trajectories that start at 0 and end at z. And that's the functional if I insert this. So I had phi dot minus b, so this is u dot plus gamma u squared. And this one you can solve, and that's the answer. This is the solution to this calculus of variations problem, if you want. And here's the corresponding trajectory. So this light blue line is the u star, that is the minimizer, and therefore should be the center of the transition tube. And this is indeed what you then observe. If I sample this system a lot of times, then I get the cloud around this, but I conditioned it, so I threw away everything that doesn't hit or exceed 1 at final time. And then I get this nice cloud around it. Actually, the size of this cloud is squared epsilon that travels with this minimizing trajectory. And I get in principle even more, namely that if I average all of these trajectories, so this is hundreds of trajectories, therefore I get a cloud. But if I take every of these trajectories individually and average them all out, then the average will be very, very precisely on this minimizing trajectory. So the average, and that's what I'm saying, it's at the center of the transition tube in the sense that there are fluctuations around it, but the fluctuations cancel out, at least in the small epsilon limit. Yeah.
So you know that the solution is going to have u of t equals z.
Right.
Well, I'm asking the question, this is because of a property of S. Is it like the convexity of S? Or something?
No, that's just the problem that I set myself.
Oh, right.
So it's like a extreme event problem, if you want. I have an Ornstein-Uhlenbeck process that wants to live at 0. Okay. With small noise, it will be very closely concentrated around 0. But I'm asking what's the probability of it not being at 0, being at 1?
Yeah.
And this 1 doesn't scale with epsilon. I'm asking 1 in the epsilon to 0 limit. So it becomes less and less likely for an Ornstein-Uhlenbeck to be away from 0.
Yeah,
I mean, it's all Gaussian, it's all simple.
But I'm saying
right.
It might be the case that the minimizer has u of big T greater than, strictly greater than Z.
Oh, you're saying bigger than or equal?
Yeah.
Yeah, so I mean, it's universally true that if I reach something bigger than Z, I have reached that as well. And reaching Z is easier than reaching something bigger than Z. Of course, there is some assumption that I need to do for my observables of what I want to do, but in this case, this is clean.
In this particular case?
Yeah, in many cases, no. Like, it's very generically true.
Sure.
Like, you need, I mean, if you have, I guess if you would have some non-autonomous thing where you can do something early and then fall back or something, maybe then not. But for these systems, for many of the systems I was talking about, the probability of reaching Z is bigger than the probability of reaching Z plus a bit.
Sure.
Because I can just do the same thing just a bit earlier or a bit later. And then I need to do a bit more, so it's right. So the minimizer of reaching anything bigger than Z will always be dominated by the minimizer of reaching exactly Z. Yeah.
Is the start territory unique?
Sorry?
Is the start territory unique?
The start.
Is the minimizer always unique?
It is not always unique. In this case, it is unique. In general, it is not unique. In all of the problems that I'm showing you, it will be unique to, I mean, there will be a unique local minimizer, or at least a nicely parameterizable family of local minimizers. But in general, you have no idea. This is the fundamental problem of optimization, of non-convex optimization, that you don't even know whether you found a global minimizer.
In that case, it's hard to interpret what you mean by the mean of all the territories. It's not in this, and the mean can be somewhere
Right. I mean, this is rather sophisticated. Maybe we should discuss this, but you are now saying there might be multiple viable channels of realizing a certain event, and you're looking at the relative weight, and that's a very interesting problem. In the epsilon to zero limit, the only thing that survives is the most likely one. So the only thing that your problem remains is that you have multiple competing channels that have exactly the same probability, which of course is believable if you have some kind of discrete symmetry in your system, like with, okay, capsizing left or right will have the same probability. If it's discrete, it's easy because you just sum them up. If it's continuous, you need to integrate them up, but it's, yeah. But I mean, for a complex system, you might not. So now let me come to what I termed the chemist's approach. So I guess in these kinds of systems, you always constrain yourself to a gradient diffusion in the potential landscape. Maybe you have momentum, but here I'm saying overdamped. So I have an ST that doesn't have a generic B. I have it to be the gradient of a potential energy. So my STE is reduced to this one. And for this one, we know that the invariant distribution is the Gibbs measure, and we have all of these. I mean, I don't have a beta, I have an epsilon, but it's all the same things that we've heard. I have a potential energy landscape, and this tells me everything about the likelihood of being at any point, because this is the invariant distribution of this process. So the intuition here is that I have some kind of landscape with minima. These are the black regions, and there is a dot in the middle, which is the stable fixed point of these dynamics without the noise. And then if I want to transition, you would usually transition through some kind of saddle point. So here's the saddle point. I think all of this intuition is maybe shared by many people that are doing these kind of things. For example, in molecular dynamics, that you're saying there is a relevant saddle in the middle, and transitions will go through it, and they will definitely go through it in the low temperature limit. Now we have a procedure that this is just a special case of what we derived, so it should come out. And that's what I want to attempt to do here. So in particular, if we compute this minimizing trajectory, we will observe that at every point, this trajectory is parallel to gradient u. It's either, if I'm climbing from here to here, it's either pointing exactly against it or it's pointing exactly with it. It's very hard to see, but of course, on this point, the vector field is pointing exactly in the same direction as the white line. So in some sense, it's a heteroclinic orbit from fixed point to saddle point, and then from saddle point to fixed point again. So why is the case? Well, I can look at the what's called Freital-Wenzel rate function that I've written down. Now B is minus gradient u, so I have not phi dot minus B, I have phi dot plus gradient u squared. Obviously, this is minimized by phi dot equals to minus gradient u, because if phi dot is minus gradient u, this whole thing is 0, and this whole thing can't be less than 0, so that's the minimum. It's of course true for any vector field B. The deterministic trajectories, those that don't need any noise, are always probability 1. If I'm asking what's the likelihood to go from this point to that point, it's 0 action if there is a deterministic trajectory connecting the two. So this is true for everything that happens after the saddle. I just need to slide down, go downhill. This I can do at 0 cost if you want. I don't need to do anything because I can just pick phi dot to be equal to gradient u. There's maybe an inaccuracy because it will need infinite time, so maybe this is true in the T to infinity limit.
But what about the portion that I need to climb uphill? Well, I can do the following computation. I take this rate functional, phi dot plus gradient u, and I replace the plus gradient u by a minus gradient u. And then there is a correcting term, which is just 4 times the mixture term, right? So phi dot minus gradient u, 1/4, plus gradient u times phi dot is phi dot plus gradient u, right? This is just easy formula. So then the idea is that this is just a line integral. This is in some sense a conservative vector field, and I'm saying integrate this along some curve. So this is just the potential at the end point minus the potential at the start point. This term is invariant of which phi I take. It only depends on the endpoints. Well, at this point, now that I have free choice of phi, I can also choose to be 0 if I pick phi dot to be plus gradient u. Then this point, this part will be 0, and this part is all that remains, and it just depends on the endpoints. So what I'm concretely saying here is that if I'm going downhill, I just flow along gradient u. If I'm going uphill, I'm exactly going the opposite direction. Not minus gradient u, but plus gradient u if I want to go uphill. And that's, of course, recovering time reverse the symmetry of an equilibrium system. This process with the potential landscape is an equilibrium process in the sense that its time reverse process is the same as this one. So this is the argument through this large deviation or fundamental theorem of the connecting pathway between two local minima in a potential landscape must always be heteroclinic orbits because they either are exactly against the flow or exactly with the flow. And therefore also they must go through the saddle because that's just the cheapest point to go from here to here if I just go against the gradient flow. And the total cost will then be u at the end point for the uphill portion, which is the saddle point, minus u at the starting point. So this is, of course, what many people here know. Transition paths are uphill or downhill just gradient u, just with the sign flip. But in particular, the probability of transitioning is E2 minus epsilon to the minus 1 times the potential difference. This comes just from the fact that we can, on paper, integrate out the Freytag-Menzel action along the minimizing trajectory because this part is independent of the trajectory. We know that this is true. This is just Arrhenius law. And in this case, you can actually say much more. You have Eyring-Kramer's formula, for example, that you know that the transition time that you expect also scales like this, with the minus being disappearing. And then you can actually compute the prefactor as well. So in these cases, it's actually very easy in comparison to compute the most likely path. You have these naturally elastic band and string methods that do exactly that, and that would converge to this white line. But this is using the fact that these are heteroclinic orbits, which in general is not true, but it's true here. So in some sense, because I think this is a setup that many people here think about, this is a surprisingly strong simplification of the general setup. Instead of solving a global optimization problem, I can just look at the endpoints. I don't need to solve any global optimization problem. This fails quickly when the vector field is not gradient. So I just have this slide for fun. I'm not sure whether this is relevant for many people. Look at this vector field, and it looks not very it's a specific vector field that's just chosen in a specific way. I have 2 points, A here and B here. I have a saddle point here, and I have a mirror of the saddle point down here, but I don't plot it. Would you say the most likely transition path goes through the saddle or not? So I'm not sure whether anybody has an intuition on this system. I mean, okay, maybe no one. Fair enough. So you can solve the whole thing, minimize the Freytag-Menzel function for this thing, and here's a trajectory that you would get. A goes to not the saddle point, but to this like maximum point, totally unstable point, on the separatrix, then traces along the separatrix to the saddle point, and then goes back down to the other point. So this portion is where you pay, because you're going against the flow. But then once I hit the separatrix, I slide down at 0 cost to the saddle, and then I slide down at 0 cost to point B. This looks highly artificial, and in particular, this is not the only minimizing path, because, for example, this path that goes the same uphill portion, well, then chooses a different direction to slide down, has the same cost. And there is an infinite family of minimizing paths that do the same thing, and in particular, most of them will never see the saddle. So Eyring-Kramer's law will certainly fail for that. Like the curvature around the saddle, or the Hessian around the saddle, is irrelevant for this problem. And that's only 2D, it's very simple. So all of these intuitions that you build up about an energy landscape and you transition through a saddle point is very quickly broken for vector fields that are non-gradient.
So,
Yeah.
can I ask a question? Before you said that phi should be differentiable. Here it looks like.
Well, these take infinite time.
Sorry?
These take infinite time. Phi is differentiable. But did I say phi is differentiable? Absolutely continuous. I mean,
Okay.
yeah.
That's continuous.
Yeah.
Okay.
But I don't think it's necessarily a barrier, all of these arguments, because everything that's not continuous, you can just replace. I mean, you say has infinite rate function, and then you're still fine. So there is, of course, an underlying question on whether we can still talk about, for these systems, there's the B, is there still something like a potential that I could define that takes the role of the scaling of the probability? And indeed there is. This is called the quasi-potential. So it's still true that the probability of transitioning from this point to that point scales like an exponential, where in the exponent I have the difference of two potentials evaluated at the saddle and at the fixed point, and with the right scaling in epsilon. But V is the so-called Frey-dimensional quasi-potential. And that's a function of the starting point and the end point. And it's the minimum over all trajectories of the rate function, and then also minimizing over all times. This is basically a function that tells you how difficult is it to go from x to y for any pair of x and y, because this is the difficulty of going to x to y in time t, and then I'm minimizing this over all times as well. So you can still define such a function, but it will no longer be a nice potential because it's a function of two arguments. And in particular, b is not the gradient of this, but you still have this Lyapunov function that somehow decays as you go to a fixed point and so on. In general, this is very hard to do. I mean, this is still a simple system. Like in general, you could say they don't even have fixed points. I have limit cycles or chaotic attractors and whatever, right? You can do a lot of things that break a lot of things. But that's the generalization that you could, for example, make. So you can still talk about potential energies in this case, but it's a bit more complicated.
But is the nice part of having quasi-potential, say this relation, arbitrary times to transition?
The quasi-potential is helpful because then you can phrase laws like this. There's still a potential barrier that determines the scaling of, for example, mean first passage times and things like that. So the details become more complicated, but this, I mean, because it might not be differentiable and so on. But in principle, that's its purpose. It takes the role of the landscape because it's just saying how difficult is it to reach every point. But you always have a reference point now. Yeah. So I think the basic idea is if I would have 3 minima in a gradient system, the probability of going from A to B, B to C, and then C back to A, you can't have any probability fluxes. But here I can. I can say if I'm in A, I'm more likely to go to B, and if I'm in B, I'm more likely to go to C, and then at C, I'm actually more likely to go back to A, and I have like a global current and these kind of shenanigans. All right. So I now want to say this is the restriction and then subsequent maybe generalization of how you would view this if you are in detailed balance and you have an underlying potential landscape. So let me now say how maybe a physicist would view this. And you just said that maybe you've seen path influence, but maybe not, but this is what it will boil down to. So how would you compute the probability of ending in B when starting in A, if you have a given system? So an easy way to view this, I mean, physicists, I guess, double slit experiment or something. I have an A here, I have a B here. The probability of going from A to B is either I go through this x1 or I go to this x2. This is just saying probability of A to B is probability of going from A to x1 to B plus probability of going from A to x2 to B. And of course, I can pick many such gaps, then it would just be a sum over all possibilities. So what I'm building up to is the path integral, and maybe you all have an intuition about this, but let's maybe go through this. If I have a single constraining plane, then I need to consider all of the gaps in that plane. If I have more than one, then there is a combinatorial explosion of paths that I could take. I could maybe go to x1 first, then to y2, and then to b, and so on. But the probability is then just a double sum. I need to sum over all openings that I have on this plane, and then all openings that I have on that plane, and the probability of going from a to xi to yj to b. And of course, I can drive this further, get a triple sum, drive this further with infinitely many, if you want, infinitely many planes where I have a finite choice of possibilities. Then I get an infinite sum where I have index I1 up to IN and go to infinity and have all of this transition probability, like going from my point A to all of the in-between points that I can do. So here still the choice of gaps was discrete and I just sum, but of course, okay, it's actually a finite gap and I should need to integrate. The probability of going from A to B is the probability of going from A to any of the x's and then to B, so it should actually be an integral. And if I have 2 of these things, It should be two integrals, right? The probability of going from A to the next one, to the next two, to a B, and all of them can be continuously distributed between the gaps that I have. These are macroscopic gaps. So this would be an example trajectory that is straight until it hits the first plane, and straight, and then going down again. And of course, then the logical last thing that you would do is to say, I now have infinitely many continuous points that I could be, and I consider all the trajectories going from A to B. So you would have an infinite number of integrals, and I consider always the probability of going from A to the x1, to the x2, to the x3, which can all take continuous values, and there are infinitely many of them. And that's exactly what's often called a path integral. So what I'm saying here, the probability of going from A to B is just summing of all paths that connect A to B, weighed with the probability of observing this path, right? So if you phrase it this way, it sounds stupid even. All I'm saying is the probability of observing anything is summing up over all ways that this anything can happen and weigh it appropriately with the probability. Of course, this object is highly non-trivial because it needs to be appropriately normalized, and probably there are divergences and you need to renormalize everything and so on. But that's the setup that I now want to be. If I have the probability of observing a path, I just integrate over that for all paths that do what I want, and that gives me the final probability of doing what I want. So what's missing? Well, what's missing is what is the probability of observing any path? I have a system. How do I deduce how likely is it to observe any path? With this system, the one that we were talking about, x dot is b plus some white and time Gaussian noise. What is the probability of observing this white and time Gaussian noise? Well, and that's, I guess, recovering Schilder's theorem in a sense. The probability density of any Gaussian variable is just e to the minus x squared. Probability of two random variables is the sum of the two, e to the x squared plus y squared. Probability of n of these is e to the minus 1/2 sum over all of the xi squared. So with some hand waving, I can say the probability of observing a Brownian motion is e to the minus 1/2 integral over eta squared dt, right? So this, I mean, I'm not sure whether physicists would do this, but maybe they would. This is, of course, Schilder's theorem, right? This is just replacing eta with phi dot, because I'm actually not operating on the noise, but on the increments in Schilder's theorem. But it's exactly the same thing that I'm saying, well, Brownian motion fulfills the large deviation principle. I'm just saying trajectories of the Brownian motion are Gaussian, distributed according to a Gaussian. The probability of observing any eta for Brownian motion scales like this, with an infinite normalization constant in front, I guess. But fair enough. There is no density in path space, of course. But if there was one, it would be this one. Right? Yeah, we don't need to be so precise because now we have the physicist stat on, and I think it's still good enough, right? No, I mean, it is not. It is. I think it's helpful. So now I can just go ahead and say, well, if I know the probability for a noise, I know the probability for a path. I just solve this one for the noise, right? If x dot is b plus eta, then eta is x dot minus b. And then I just insert. So the probability of observing any path is e to the minus 1/2, and then the time integral of x dot minus b squared dt. This is just the Friedland-Wenzel rate function, right? You just solve for the noise, and I say if I know the probability for a noise, I know the probability for a path. Maybe there is a Jacobian. I don't know how much you did on Tuesday. And there are a lot of divergences happening. As I say, this is not, there's no density with respect to Lebesgue measure in path space, but this is still the weight that I guess intuitively we should take. So I guess now we have answered our question. The probability of observing a transition from A to B is just a fat path integral where I sum over the probabilities of each of the paths, and the probability of each of the paths is given by e to minus the Friedland-Wenzel rate function. So here, in physics, you would call this functional an action, and this is a path integral over e to minus an action. So this is all nice and everything, but of course it's useless because you cannot compute this integral. Maybe you would say, yes, you can. You can just sample it with Monte Carlo, and maybe that's true, but this is the setup that we started off with anyway, that these would be hard to sample with Monte Carlo, these path integrals. But now I go ahead and say I make the event rare. So instead of looking at the noise, I scale my noise to square root of epsilon and look at the limit epsilon to 0. So if I just insert this, I get the same formula. I just get a 1 over epsilon in front of the path integral. So in front of the exponent of the path integral, I now have the weight e to the minus 1 over epsilon s of x. What do we gain then? Well, then we can do, I guess, what people in quantum field theory like to do and do a saddle point approximation or a semi-classical limit. This would be an h bar is small. This is what we do. We use the Laplace method. The Laplace, maybe everybody knows the Laplace method, I'm not sure. Well, let's just recall the Laplace method. If I have an integral of this form, f is now just some function, e2 minus 1 over epsilon times this function, then in the epsilon to 0 limit, this is just e2 minus 1 over epsilon, this function, at its minimum. Why should this be true? Because if I Taylor expand around the minimum, f of x star plus h is f at x star plus h times f prime at x star, which would be 0 because we are at the minimum, plus second order term and so on. F prime at x star is 0. So if I insert this here, I can just draw out this at the minimum, and what I remain with to this order and the higher orders I just neglect is a Gaussian integral, which is just some constant. So I'm saying all that comes out is some constant times e to minus 1 over epsilon times the function evaluated at the minimum. So this is the only thing that we now need to do and apply to the path integral in a giant leap from 1D to infinity. So I say sample path large deviations are exactly that. They are an infinite dimensional Laplace method, or they are a saddle point approximation of the stochastic field theory in the small noise limit. The property of going from A to B, which is this path integral, in the limit of epsilon to 0, is dominated exactly by the action at the minimizer. Nothing else to do. And I need to minimize this over all paths that do what I want. For example, transition from A to B. Right? So this is how you would phrase this maybe when you would do saddle point approximation of path integrals. But I guess now we have our physicists set on. We can as well continue to be physicists. Who here has taken classical mechanics? A lot of people. Half, maybe. Perfect. So what I conclude is that for this stochastic differential equation with weight and time and some covariance in space, I have an action functional in this A norm. And now I would say, well, it's an action functional, it integrates over something. I call this the Lagrangian. Lagrangian phi dot is just phi dot minus b squared times 1/2. We are interested in the minimizer of the integral of this Lagrangian, and you would often call this the instanton because it's, I guess, quantum chromodynamics lingo, where you're saying this is the instantaneous transition path from one minimum to the other one. But if we have a Lagrangian, there is a Hamilton's principle, and I can define myself a Hamilton. So I define myself on top of my trajectory phi, an appropriate conjugate momentum, and the connection between the Hamiltonian and the Lagrangian is just the differential Legendre transform, showing up yet again. So I just need to minimize over all of the phi dots. Phi dot times theta minus L. This times is, yeah. And I can do that for the specific Lagrangian that I have here, and this is what comes out. It's b times theta plus 1/2 theta times a theta. So this is the noisy part. This is the dynamics part. You can interpret a lot of these things. This is a quadratic Hamiltonian because the noise is Gaussian. So the square here on the theta is exactly the square that you have in the Gaussian noise. You can write these things for Poisson processes. You can write these things for many other processes, and then they wouldn't be square. But for all of the STEs, this is the form. And then I can say, instead of minimizing globally this functional, I can just solve the equations of motion of the corresponding Hamiltonian. The minimizer of the action solves the Hamilton's equations of the corresponding Hamiltonian. So I guess this is either calculus of variations or classical mechanics. Looks like I lost everyone.
What is A?
A is sigma transpose. If I here I wrote the expectation of eta I, eta j is aij. But it was, I think, sigma transpose before as well in the Freital density. Yeah? Well, you can do that as well. It's equivalent. Yeah. So that's, yeah, I mean, all of these things are equivalent. I just chose to not write them because this is, I guess, a bit more educational in what I'm about to say. But you're absolutely right that you can write down an Euler-Lagrange equation, and then you wouldn't have any conjugate momentum. You would express everything in phi and phi dot. So this would be dl by d phi minus d by dt dl by d phi dot, and you would get a solution as well. So I'm preferring this one because now I'm saying this is the original equation, x dot is b plus eta. This is the field Hamilton's equations. Phi dot is b plus a theta. So I'm solving basically the same system that I solved before, just instead of stochastic noise, I have a given noise and I have an equation for the noise, right? In particular, if you have a code for this system, you have a code for this one. It's the same dynamics. You can interpret this in the same way, just that I don't have a stochastic noise. I have an optimal noise in some sense. And I have an equation for that. The detail is, of course, much more complicated, and also there is boundary conditions that need to be considered. How do I encode the final hit point and so on? I don't want to do like shooting methods and so on. But this is why I'm showing the Hamilton's equations, because this will now be the basis on allowing me to solve much more complicated problems, and that's what's happening next. So the next problem that I want to show exactly this principle on is KdV equation, an equation for shallow water waves. And this is a PDE. So it has a time derivative, it has an advection term, it has a diffusion term, and it has a dispersion term. It's a well-known nonlinear PDE example. And I imbue it also with stochasticity, so it's an SPDE. But don't get scared, it's not a singular SPDE because my noise is smooth, so it's not white in space, it's just white in time. I have some noise covariance in space as well. So this is an equation that's used to describe shallow water films, for example. And I want to ask, what's the probability of observing at arbitrary point x equals 0, at arbitrary point time t equals capital T, an exceedance of the amplitude of z, a large wave at a point. So at location x equals 0, and at time t equals capital T. So for this equation, I can write down the equations. So the Hamilton's equations for the given Hamiltonian corresponding to the Lagrangian to the Fred and Wenzel rate functional, and they look like this. So this is again, the top one is again KV, just solved for DTU, I guess, and the noise is replaced by A times conjugate momentum, but A here is chi, and I need to do a convolution instead of a matrix product because we are in continuous space. And I get an equation for P as well, and I can solve the two. And here's what comes out. So the observer that I say is large wave at final time, and I want to estimate this probability. So I can show you what the minimizer looks like. It will now be, I guess, an animation of what behaves. I start at a field that's equal to 0 at every point. So I start with a fluid at rest, no amplitude. And then I stir on large scales. That's what the chi encodes. I only have large scale forcing. So I build up a wave at some point. And then this wave steepens due to the nonlinearity. And then at the final point, it has steepened to a very high value because that's what I prescribe. So this is the instanton, if you want, for KdV conditioned on this. Similar to the Ornstein-Uhlenbeck process where I say hit Z at time t, I now say hit or exceed Z at final time t, but it's only at this point. So the only thing that I prescribe is the amplitude here at final time at 0. And the rest just kind of like falls into place as the solution of the big optimization problem that's saying, all right, you want a high amplitude here at that time. Here is the most likely way for realizing this. Using the forcing in an optimal way that it goes through the nonlinearities that are in there, using all of the instabilities that come about, the steepening from the advection term, and then the dispersion term that transforms this into a high overshooting oscillation, such that the wave is exactly located at the final point. So this is the most likely high amplitude wave. And then I claim that I can deduce from this the probability, and that's the next slide. So here I'm comparing basically epsilon equals to 0.1. Points are Monte Carlo if you want. I just integrate, I guess, 10 to 100,000 times the KdV equation with random noise. And here's the probability of exceeding a certain wave height. And then dashed line is e to the minus epsilon to the minus 1 times the action, appropriately normalized because I don't have the prefactor information. And in the tail, this kind of fits very nicely. So the idea here is that as the event becomes rare, the probabilities scale exactly like a large negation principle, even in this PDE case, contracted to only the final point. So this is only possible to solve nicely on a small computer because I'm using the Hamilton's principle and doing forward-backward sweeps of the Hamilton's equations. Right. So this problem is not small anymore. This is NT by NX, 1,000 by 4,000 points. So if you hand wave, then this is the 1,000,000 degrees of freedom optimization problem. But okay, it's also not big. I don't know whether that's big or small. But this is the number of degrees of freedom that I formally have. So now I want to get back, and this is maybe now, so maybe any questions for this, or is this good?
Just because you mentioned the prefactor and the iron front, so that doesn't depend on the epsilon?
The prefactor.
Yeah, as in.
The prefactor does depend on epsilon in a precise way. I'm not sure whether I will get to it. That's most of what I'm currently doing in terms of research, but it's more complicated. Yeah. So it would be interesting to get the prefactor, because then you wouldn't need to do any fitting. You would just get the probability, right? You would just ask, what's the probability? Here's a number. That would be great. Yeah. Okay. Maybe time for another 10-minute break. Would that be great?
Yeah.
Yes.
We come back to the
Yeah.
slide.
So I'm not sure whether I can. Where are we now?
I have to run. I'm
Yeah.
sorry. So
Yeah, no worries.
thank you.
Thank you
I'll
for
see you
coming.
soon.
So
Yeah, see you soon.
I'm not sure I can explain it even. This is very standard classical mechanics, but I have never taught classical mechanics. You have a Lagrangian?
You want to minimize something of
Right.
phi,
Mhm.
and then what are you saying?
I'm saying define a new function, h, that's no longer only a function of phi, but also of theta. That's the
Theta is the velocity. Theta is the velocity.
theta is the momentum. Yeah.
Yeah.
Velocity I would call phi dot.
Oh yeah, sorry. Yeah.
Right. But instead of viewing it in position and velocity space, you view it in position and momentum space. But this is much more abstract than usual classical mechanics, because the Lagrangian is much more abstract.
Yeah, this is something.
Right.
Phi is defined.
Right.
Here you minimize over the derivative of phi. So how many possible phi of 1?
Yeah, so you view phi dot as an independent variable in this transform.
Okay.
So I insert a phi dot that doesn't correspond to the phi of this function.
It's something.
Yeah, so I should maybe write min y. Y dot theta L phi comma y.
And what is the connection between these and these?
So
Because this, okay, I guess this is just how the Hamiltonian dynamics to preserve these ideas.
yes, this is true.
Okay, but what is then
So the high level connection is that the solution of this pair of equations is the solution of the Euler-Lagrange equation. And you can derive from the Euler-Lagrange equation these equations or the other way around. But it simply is inserting another variable and it's
checking only the first coordinate? Because, or
so theta is phi dot minus b.
okay.
Because I'm just because if I solve for the other one, it's phi dot equals b plus theta, right? I mean, if a would be 1.
Okay, the details I have to check, of course.
Right. But if you look at dl by d phi minus d by dt, dl by d phi dot, and then you insert this, you recover the same equation. So the solution of this pair of equations is identical to the minimizer of the original minimizer.
Because of the connection between these, that one, coding wise.
Yeah, so it's not so trivial to say, well, this is better, but most importantly, the original Friedel-Wenzel action had an a to the minus 1 in it. But you need a to be invertible. Here I don't need
Is it not? A as in sequence of matrix.
Right. So it is invertible if I'm forcing every mode. Right. Of the forcing. So in this problem, and in generally many problems in physics, you would only force a few degrees of freedom. Like I have noise only on large scales for the waves, not on small scales. Or for climate, I would force the solar constant. I wouldn't have noise on every single degree of freedom in a climate model, right? Only a very few that I consider noisy. Yeah, exactly. So you can't invert. So Friedel-Wenzel theory still makes sense, but it's very awkward because you need to replace the inverse with like a pseudo-inverse, and then you need to do stuff. So there is a numerics background behind this as well, because then Friedel-Wenzel you would need to solve through penalty, where here this comes out automatically. Instead of saying maybe I have a theta that's somehow the optimal noise, and even if this is active on every degree of freedom, if A is not full rank, it will just set all of these things that are unimportant to 0, and they're just left free, and I don't care about them. Yeah. And then I can just integrate this one, and it's very easy. There is more secrets to it, because and this is also a traditional optimization technique, and maybe we'll get to that, because I mean, the physicists would call this the conjugate momentum, because it's conjugate to your field. A numerical optimization person, or maybe a machine learning person, would call theta the adjoint field in some kind of backpropagation line. So I'm phrasing my gradient as a forward-backwards field. Okay, this equation needs to be solved backwards in time. It's not obvious, but it must be. And whenever you evaluate this equation forward in time and then this equation backward in time, you have evaluated the gradient once. Instead of globally doing so, which is then I need to resolve space and time. And here I only push something forward and I push something else backward, which is much cheaper in memory because I basically can discuss away all of time.
Do you know, Sebastian told me you have some lecture notes on these things?
Yeah.
Can I find them from your website?
Possibly. I'm not sure whether they are public. Yeah, they must be. Yeah. I don't know. Yeah. Yeah. I mean, maybe you write me an email. I'm not sure whether they. If you don't find them, you just write me an email.
Thanks a lot.
General principles, mechanics, numerical machines.
Yeah.
Is there also some stuff?
Yeah, you can write all of this.
I'm aware. I've never really looked at them. And you're talking about numerically.
Yes, this is beneficial for me numerically for this stuff. For experiment problems with where this function phase.
What about these numbers that go in single BD?
This I've never seen used anywhere. I'm not sure what the difference is if you boil it down to what we actually need to do. I mean, all of these are good, right?
Yeah.
So I'm not sure whether there's something underlying to say, okay, here's my I'll go ahead and solve it, whether the okay, that's the kind of reduces because the Hamilton equation is the Hamiltonian gradient. So do you have these things available? If not, then you need to function in this form.
Yeah, I'm just wondering what kind of why. Because this is for derivation.
Yeah. So I have to know the Hamilton equation. It comes always up in the derivation, but then it's the beginning. It's complicated, but this is not like more level. It's probably very hard to solve.
Do you end up crazy
Is it not? In my lingo, would it not be BTS is equal to H at phi gradient S?
Yeah, pretty much. The issue is that sometimes your S, if your S has a gradient of potential energy, you end up with testing it in terms of.
Yeah, this would be true here as well. The gradient phi S I can compute, right? But I think what you run into this is that this is then solved as a function of space and time as a full field, and then relaxed somehow. I don't know. Yeah. Well, this one is forward, backwards field from the PE. I don't need to keep track of every point in time. But yeah, I mean, yeah, I don't know whether something can be done.
Taking epsilon down to 0 is like an interesting problem would be to find out at what stage is epsilon terms multiplied how small epsilon is to be before these other rates, these other popping rates. So what temperature are you?
Yeah, so generally you can't answer this question. But locally you can. So I'm thinking about if I view path space now as an action landscape, I want to minimize globally the path that has been action. I imagine like my minimizer to be a local thing that has. So I would look at the curvature around the minimizer. But this is passive, so I'm talking about like what is the second variation operator around the meaning of the action. And then the eigenvalues will tell you like how dominant fluctuation. If it's very flat, then this fluctuation. I mean, maybe we'll get to that.
Oh, are you actually going to
So yeah, you need to look at the second variation, and you somehow need to compute its determinant to get like the volumes, the paraboloid cluster is really volume. Yeah, so you need to compute with things like this, right? Like how do you?
You know, the Kramer rate difference is basically people don't use that.
Fair enough.
We use the transition state theory speed factor, which also has a fudge factor in it. It's right.
The arguments are different. But I have people use that even in fact like other molecular dynamics.
Not that I do this stuff all the time.
When I think they can shepherd or someone else giving an automatic stability and saying, oh, I want to find all of the same points. That's what you do as well. Right?
Yeah.
You know what you mean? I
can charge money other forms.
So you have because just behind from down
It's like the old like small that's why
if I want to solve phi dot equals P of phi, of course I can minimize phi dot minus P of phi squared. But I mean, this I can just integrate. I don't need to minimize this.
my problem is to find B, like the typical thing.
Okay. For me, B is always like, okay, that's the system, it's just given. So you want to learn a dynamical system or something.
I have a random system.
A random system.
Like, yes.
But you know the statistics.
Yeah, I know how it.
Right. So then it wouldn't be in the B, it would be in the noise cluster.
Yeah. Okay. I know that it would converge to something deterministic,
Right.
like something like this without the noise. So I want to find this speed. So I'm just saying that for that, if I can find the typical by minimizing this integral and then find what it converges to then.
Yeah, so maybe we should, yeah, I don't know whether that's possible, but it's very different to us.
The all in which let's say
All right, yeah, you go ahead then.
Let's start again. I'm gonna adjust that 1 second.
Oh, you do the recording again?
Yes.
Yeah, so thanks for everyone for staying for the last hour.